Awesome. Greetings, everybody. My name is Kevin Kawchek. I'm the founder CEO of Chemical Q Device. This is discussion 90, July 6, 2023 for quantum algorithm and deep learning pairs for medical analysis. This indeed is a Promethean task. It's outside the box compared to classical computing. And I break it into a couple pieces. So you don't want to use quantum computing unless you have to, right? And then in order to get to that step, you have to know the weaknesses of deep learning, the strengths of quantum computing. So in specific, a lot of people use quantum computing for these principles. So it's called superpositioning, entanglement, interference. There's a type of parallelism that's different from classical computing, but simultaneous parallelism. Now, this all is happening over a quantum bit or qubit or some qubit, most commonly quantum bits. And you get something called expressibility, which is a wide range of quantum states. So this is sometimes desired to put a bunch of the data, and this is the component, especially in medical, is you want to find ways of putting medical data sets that are expressed over the surface of the quantum bit, okay? Or it could be in the volume of the quantum sphere as well. And another thing desired is basically to get generalizability, which is over a wide range of problems, scalability, so large number of inputs and complex problems, and then get that performance. So there's two main camps in quantum computing. Some want, from a theoretical perspective, a better, performing algorithm on paper. But we don't quite have those quantum computers because they have too much error, and they can't handle a lot of data without the problem not working well, or it just doesn't work. And so the other way is to look at the physics of qubits and qubits and these quantum spheres, and basically to find to have a better understanding, because I'm going to share some papers here, is how exactly you can separate medical data sets over, surface of sphere representing a qubit, over the volume of the sphere, and to do that in a more predictable way in a complex machine learning environment where it's picking up the speed for, on the classical end, something it can do better quantumly. So it might not necessarily be something, especially in the near term, that's super fast. Although if you have a GPU-assisted quantum simulators or multi-GPU, that can help to boost things up, basically. So we have more people coming in here. And you've heard me say that time and time again is you want to look for the noise-free approaches, especially if you have tons of data, and try to speed up the lack of the simulations. But there's types of algorithms out there that you might have a quantum advantage on, and by the time you have run them on a quantum simulator, you're losing a lot of that advantage. So also look for those opportunities as well, where your net is still speeding things up and perhaps still getting that performance benefit of mapping data over a quantum bit in a specific way to get a classically harder inductive bias, something that already exists, practically usefulness in quantum, and does not induce training issues. So I could go in a separate lecture, machine learning, with a lot of this. And that's still the case as the quantum circuit is happening. So the title of this, as more people come on here, is deep learning pairs. So you have an algorithm and deep learning pair. So when is the deep learning network in need of some performance benefit in accuracy or loss, or it's basically the way it processes data? When is that the case to insert that? And the four papers I'm going to put in the chat here. So there's four I kind of picked out. The first one is Seth Lloyd, Maria Scholl et al., and others, 2021 quantum embeddings. And it's kind of reflecting a lot of what I'm talking about, or what I've learned from. And it's a field called quantum metric learning, where you're just training the embedding layer of the entire quantum circuit, because that, if you're taking in classical data, that's very important. So I'll put these four in the chat here. And I wouldn't say, especially with machine learning and incorporating quantum algorithms for a very effective pair, say, okay, we have 5,000 images, based on this, ResNet 34 convolutional neural net that's classical. We know exactly what to put in, say on the quantum network end. So here's the four that are going into the chat. And a lot of this is stitching the pieces together still with quantum, right? I wouldn't say, I wouldn't say, I would say few, if any, people have a really good understanding as far as the amount of big data and medical, especially EHR data or images and the exact quantum algorithm. I would say there's still a lot of experimental work that's being done, and you could kind of go through those as well. Now, the second one I want to focus on, this just came out last week, and it's by Casper Guyurek, Vedran Dunko, exponential separations between classical and quantum learners. So in effect, classical data. So it's June 2023. And if you joined the discussion earlier on, like months ago, I talked about this concept of quantum data, and then you also have or you have data and you have algorithms, and you have different combinations of classical and quantum. So it'd be a CC, CQ, QC, QQ. Now, another struggle with the whole quantum machine learning is the nomenclature, because a lot of times if you were to do a Google search, you would see that compares data versus algorithms. But in this specific paper, so this would be the B paper, B1, is they refer to classical, the C, as classically learnable, i.e. like a deep learning net. And it's split over machine learning probability distributions normally. And then the Q represents quantumly evaluated hypothesis class. So in the B1 paper that I shared, it's basically using classical data, as far as I know, for the bulk of the paper. If you look, I think it's like the second sentence in the abstract. And that's why I really read this paper and continue looking at it. And it's a little bit more abstract. It won't tell you the exacts, like this is the exact algorithm, but it's more like it's the theoretical approach of like, okay, this learner that's classical, can be supported, with a quantum algorithm here. And then the paper C, the LaRocca M et al., it's a theory of overparameterization, and it's shocking. It basically says that if you overparameterize, which is typically a bad thing in classical, is that you can negate some of the ills associated with quantum computing. So that's a Los Alamos National Laboratory paper right there, 2021. And then the D paper, Peters et al., generalization despite overfitting. So it's basically saying in this one that if you know machine learning, you have a training data set, and then the line that's going through these points should generalize. It shouldn't try to pick out each of the points, which is called overfitting. And it should have some general trend that like an underfitting curve just doesn't ever get to. But they found that in quantum, what happens sometimes is that you can have benign overfitting. So it's going to pick out points while it's generalizing the data. And these are just one of the things, that is basically, it's being further understood in quantum. And I would say in all these things, it's still a lot experimental. I just did quantum transfer learning versus 3 other classical networks. And it appears between 44 classes or 10 classes that the quantum network is helping to separate data, but it's doing so slower. That's to be predicted. And sometimes there's issues like I can get to 20 qubits, but I can't get to 88 qubits because that's, based on the author's guidelines of these, ratios between qubits and number of classes. So, I put those in the chat, and then feel free to take a look at them. And I would say, it's really a game of literature at this point. Like some will come out. I mean, even the quantum embeddings paper is kind of big because I can't fully replicate it, but I can understand it enough to say, okay, this algorithm that I have that's more efficient than the original algorithm is getting better loss or, lower loss and higher accuracy compared to, a lot of the other algorithms I would try. So you can do deduction like that. And it should be interesting because, it's definitely people want to incorporate even more of this quantum computing into the pairs associated with, a quantum algorithm and then deep learning. So it's just, I would say it's off to a very good start, and it'll also get better. as far as like the diversity of different types of algorithms going in, say if you have one that's more in the kernel of the convolutional neural net, or even doing things with transformers I'm trying, or is it more so, is it like towards the end, so it's sandwiched in between two classical layers right before the final classification. So you'll see that type of diversity, I think so as well. Any questions or comments? So as far as, on the medical, and then also kind of like this hybrid environment that, maybe a year or two from now, you'll have, recommended quantum algorithms and tables, so you use this quantum algorithm for this deep learning net, those types of things. I think that we'll start to see those eventually. So feel free to unmute or unmic. I see a couple people from returning, and then also Mohammed or Risky, if you have any questions or comments with this. Kind of interested, especially on the data side, other types of medical data. I mostly do with the images, but I've seen BERT transformers with quantum networks as well. So yeah, feel free to unmute, or you can also come on. I posted some papers in the chat, so if we get, we could revisit those a little bit later. But I'm just kind of curious as far as like those that have machine learning experience, what they're excited with quantum with this. And then, so we also have Ron or Anand. Feel free to unmute yourself, or you can come on as well. And then if not, we have George or Edwin. So you should, okay. So, and you could always post in the chat too. So it's definitely an exciting field, I would say. And you don't want to run too much, right? Because like, I wouldn't say, it's not 100% field yet, but it's to the point, go ahead and run quantum circuits as long as it doesn't take too long inside other models, and then kind of experiment with it to see, number one, which algorithm works better here in this pair? What are known deficiencies in deep learning basically as well too. And I also took a look at some other things here. So you have, so the breaking article that I kind of shared, and then some demos as well. So these are interesting because these are Qiskit, and these are basically, penny lane type demos. And they have quantum circuits in that. A lot of the time, they don't need to be that big. It just depends on that task and what you're trying to do. If you see the term fully entangled, a lot of times with today's simulators, that's an issue because of, number one, speed, and then barren plateaus, those types of things. So these things are getting worked out, I would say, through literature as well. And so I put some of those in. So yeah, the demos. And then last night, and this is kind of awesome, I found this Google, I'm not on Google Circ a ton, or, TensorFlow Quantum, those types of things, but they have a qubits demo. So for those that don't know, you have qubits, which are zeros and ones, qtrits, 0, 1, 2s, q-quarts, 0, 1, 2, 3, and the list goes on. So I got up to 10. So this is later last night, just like how I got the q-quart to work, so the 4 different levels or dimensions. And then, so the 10 worked as well. The issue is the matrix gets to a 10 by 10 for, like, say, a knot, or it's basically equivalent to an X gate, similar to classical. So your matrix expands, right? So as your dimensions expands, but this opens up a whole field, right? Because if you can do it, even if it's simulated and catch up with the speed with quantum simulators and multi-GPU quantum simulators, those types of things, you can perform prospectively a task such as, like, if it's 4 q-quart, a 4-way classification on a q q-quart, as opposed to having 2 qubits. So there's advantages, right? So there's speed advantages, there's RAM advantages on simplicity of circuits and not getting into 2-qubit gates and 3-qubit gates and entangled circuits, those types of things as well. And feel free, if you have any questions, feel free to put it in the chat. So it's definitely, I think even this summer, we'll see a lot of stuff. I speak more on like I take, these online courses, and then especially the literature too, that, I want to experiment with the things that are working, like with, medical data sets. So it's, definitely an exciting field to be in, I would say. And then I also, so if you're just getting started, there's another set here of 3. So if you start off, so if you're a mathematician or if you're good in machine learning, you want to know theoretically how fast the algorithms are. Are they polynomial speedups, quadratic speedups, exponential speedups? And a lot of times you'll see that, especially in the last one, quantum algorithms and speed, there's certain types of speedups that remain linear in time and say GPU RAM. So, and you could do certain tasks. So say if you're not looking for this exponential amount of information from entangling, and more so the routing of data sets over different qubits or qubits, those types of things, that you can accomplish, in my mind, and based on literature like the Seth Lloyd and Xanadu works, you can accomplish a lot with these linear, in time, linear in amount of RAM. So that would be that last one, I would say. Awesome. So Edwin says quantum transfer learning. So I've worked on this model. It's a penny lane model a lot. Yeah, he says it's quite interesting considering the developments in classical transfer learning with large language models. Okay, and yes, yeah. So if you look on GitHub, there's BERT, quantum transfer learning. There's many different iterations on this. It's an Andrea Marie paper when he used to work at Penny Lane, and so basically in any type of transfer learning, you have an existing classical, typically, neural net that's learning off, say, an ImageNet 1000, which stands for 1,000 classes. It was a big project. And then you get those results called weights and biases. And then you can use that as a head start when you use that same exact model again. If it's, ResNet again, I don't think it has to be, but that's that pair. So, and you're inserting your own data at this point, learning from the previous 1,000 classes, this huge thing that had happened before. So you don't need as much data. Your accuracies tend to be better. Losses tend to be lower, those types of things. And it just makes sense. There's some, I guess, maybe hesitation when the ImageNet has bicycles and, you have aquatic animals, those types of things, or even, some are man-made or non-man-made. Now you have like medical images, but I think at this point it's pretty accepted. And feel free if you have anything else on that, Edwin, as far as the, quantum transfer learning. So I've seen, so the main cases for quantum transfer learning is you have your convolutional neural net, or say like transformers, VIT for images, or BERT for text. And then towards the end, you'll have another classical layer. You'll have a quantum layer, which is your quantum circuit. And then at the end of that, you'll have a final classical layer. And it's called a dress quantum circuit. So it seemed, like I said, like with my stuff, pretty much apples to apples, have the quantum circuit, or without the quantum circuit, it does, better, especially if you have a correct ratio of quantum bits to a number of classes that the authors recommended from the beginning. And then, it's going to be slower, right? So it's quantum simulators. I wasn't running on a GPU quantum simulator, those types of things as well. And anybody else as far as like different models with this? So go ahead, Ron. So yeah, so basically it really depends on, the existing. So a convolutional neural net is a standard thing in medical, like FDA approvals, the whole thing. If you bump up, or like the newer generations of neural nets are called transformers. So in specific, an image transformer is called a vision transformer, VIT. And then I had a really good VIT run classically. It's stuck in my hybrid net, but it doesn't look like the algorithms are kicking in. And I think there's some issue with, scaling, or, these different things. So yeah, it's a specific thing as well, right? Like you have to have pretty good understanding of how these networks work, the inputs and outputs of both quantum and, classical networks as well. So yeah, there's classical transfer learning, and a lot of the models will start off with say, oh, this is a quadratic boost on the quantum algorithm side. However, we don't have the quantum computer now because it has too much noise. And by the way, it's faster for like under 30 qubits just to do it on a simulator. So there's a penny lane, or there's actually a Qiskit demo with that. That's definitely out there. So I would take a look at that. And I got 100% on it, training and accuracy. It's only an 8-pixel image it's called bars and stripes. But for that specific one, I was able to change the quantum algorithm to a certain type. And if you were to run that with like a 28 by 28 image, which is common for like an MNIST kind of data set, you're talking like over 700 qubits, which we don't have that in most cases for simulators. Like if it's a specific type of, linear circuit, no entanglement, say tensor network, these types of things, you can really get higher up in qubits. So there's just, a lot of it's, I would say the more mainstream stuff isn't getting into the higher qubits, like anything above 40 or 50 qubits, say. And then, so yeah, feel free to put in the chat. I see a number of people returning from previous weeks. So we see Edwin and Anand and George as well. And it's definitely, one of those fields where it's just like, it's part experimental, right? Download the models, insert your data, if it's medical, finance, or whatever. And it's part reading papers, right? It'll save you a lot of time to kind of see where they're going from. Any other questions or comments here?
Hello. I think okay, when you're talking, kind of going back to error correction and mitigation, which is a topic that I think I attended a meetup by IBM yesterday. I think Ron was there too, and it's kind of interesting all the levels that the error could occur. The measuring in considering crosstalk, all that. I think all that was interesting.
Yeah, error correction and error mitigation is a huge field. So Edwin's talking about real quantum computers. And I know there's been some breakthroughs, I think even in recent months. I was just reading, so Google had like say a 40-something qubit quantum computer, and it outperformed their teens, maybe say like a 17 or 19 qubit quantum computer. And error mitigation is coming first, right? Because I don't think there's anybody out there that's been able to fully error correct any quantum computer. So there's different, classical algorithms that you run typically. I think for error correction, you need an additional qubit for every qubit that you have. And taking advantage of the reversible, nature of quantum computing makes it possible to do error correction. So yes, it's one of those emerging fields. I mean, the only thing I'm really concerned with is error. So that's something you don't see reported as much. So if you were to take the error or like the faultiness of any quantum computer, even if it's like ion trap or neutral atom, is that it's still significantly greater than quantum or classical supercomputer, whatever. So it makes it very challenging to do huge data sets. So, it's a really important thing for quantum computers to be error mitigated and error corrected. There's other issues, say like the algorithms that we have now haven't been tested on quantum hardware it doesn't have much error. So there's no guarantee that those will scale as well. So I would say if you watch the news, there's a fascination in hundreds of qubits and thousands of qubits, or millions of qubits, those types of things. But there's other things such as barren plateaus, local minimum, those types of things. So I personally, I've taken the approach of just using simulators, there's lightning.qubit, default.qubit, these types, and then the error simulators on Qiskit, because it helps me with running the data. It's noise free. And there's a big camp out there that basically I say, okay, well, will the algorithms run on a quantum simulator? Will those work on a future quantum computer? And this prospective approach of, the quantum computer will work, kind of thing. So there's a lot of research out there that's focused, right? Like the mindset is just focused, like the quantum computer will work. We just have to get it to work. So I think that we'll get, the biggest news for me was the multi-GPU quantum simulators on PennyLane, because it catches up on the speed, even that if you're getting that performance boost and separating data sets, those types of things. And that's today. Like you can do Amazon Briquette with those. You can do PennyLane with those. I think probably other services too. So yeah, it's just one of those things. It's, like how do you want things to work today, or like it's still not 100% sure. Like, will we have 100 qubit computer, quantum computer next year that'll be significantly better that you can use in, in a generalized way over broad applications? So it just depends on what your focus is. I say, for instance, I'll do the Qiskit Friday mornings. So this is 12 Eastern, 9 a.m. Pacific, my time. And I can't quite relate with those quite as well, because they're so focused on like, if this only worked, then all of a sudden you have this like a lot better quantum computer. So, it's that's the thing, right? If you want proof of concepts and MVPs and those types of things, that it might be wiser to run the simulators. So it perfectly simulates a quantum computer. It's just it's inside a classical computer or GPU. It's just that whole process is relatively slow. So then there's no perfect solution. Is the answer to the question. But I would say if you want apples to apples, like the physics of the quantum bits with the data sliding through, and then is that helping the deep learning neural network, for thousands of files in medical, that I think the approach might be with the simulators there.
I think most quantum computers are working better than Zoom today.
Oh yeah. Yeah, it's weird. It's holidays, it's those types of things. It's 4th of July. So did you have anything wrong?
I was just mentioning that I've been looking into quantum support vector machines. I've been finding people seem to be getting some success with that, which is very impressive, because a lot of times when you're trying to do quantum against the machine learning stack, it has to be worth it, because there's a lot of extra work getting your data encoded into quantum usable format. And if you're spending all your time doing that, then you're probably not really getting much of an advantage or speed up, especially with the small volume that we have now. Even on a 24-bit machine, it's like the amount of time you spend encoding like image data into a quantum register probably defeats the purpose if you can only do it 27 qubits at a time. But the cool thing about the support vector thing is you only call the quantum part of it once at the beginning of your training cycle, and it's a quantum algorithm that will calculate the coefficients for something that's called a kernel function. Support vector machines can be enhanced by using kernel functions, and this quantum program will quickly you can give it a whole bunch of information, and it'll much more quickly get you much better coefficients for very much higher dimensions. And so the nice thing about that is if they get real close, then your training cycle will plateau faster, and you won't need as many epochs. So that I'm finding that really interesting. I've had a chance to speak with some people who have worked on that. And it's not just a handful, but it looks like people are actually getting performance improvements. It might not be a lot, but it's very encouraging that something's happening.
Yeah, I'd be interested. Is it just for binary classifications? And then as far as data set sizes, like how high can you go?
Well, the last paper I read was by a lady who's been to this group, Emin, and she was doing using this technique to better classify. I can't remember if it's CAT scans or MRIs for pediatric patients. Apparently, pediatric test sets, for whatever reason, are not that easy to come by, and people have just sort of ignored the whole pediatric thing. I guess people's mindset is, if small children don't get brain tumors that often.
Yeah, there might
or
be some
something.
extra protection too, for
Well, yeah, but I mean, they can anonymize data easily. But I'm just wondering if but it's good that at least one person I know of is concentrating on that, because young children do get brain tumors.
yeah.
So
Yeah, it's one of those things like, yeah, I mean, you're totally right. Like if you can use these smaller quantum networks exclusively to do classifications, the one that comes to mind is data re-uploading. So it's the term they put on if you have a single qubit and you just do a binary classification that's trimming a lot of other pieces, for speed and probably for performance too. So I kind of I did that demo. It's a penny lane demo. And then I'm thinking, like, what if you could go like even higher to Q-trits and quartets and Q-quarts, and then like 10 dimensions, those types of things. And it's essentially a single wire. And it's just, whatever's passing through your, learning just with this quantum network, as opposed to like all the hybrid stuff. So it's interesting because in this, Edwin brought up transfer learning. The quantum transfer learning is based on a Stanford researchers, or it's at least one researcher. And, it has two different models. And it has one is if you freeze most of the weights of the neural net. So this is without quantum, both of these. And your results are significantly lower than if you run the deep learning net and you're allowed to, unfreeze the weights, meaning that the weights and biases are updated, every batch or every epoch. And the one that had the ones where you could update, every epoch, it's one of the better models out there, that I've seen for machine learning with images. So then in the quantum realm, you can't run that quantum circuit with the high performing transfer learning set. It has to be the one where you're freezing these, the layers of the deep learning. And then you have that quantum circuit. And for some reason in that application, you can't use it with the high performing, where it unfreezes the weights and it goes through. So it's a very specific thing, I would say. But I'm taking a course right now on edX. I think it's Linux Foundation, and it's helpful for sure because it makes me think of things, and then I'll go back and change the project board and those updates basically. So yeah, but Ron's right. Like you want to run things as lean as you can, right? And a lot of these things are just like proof of concepts. Like, will it work? And then the next step is how much better. But then, you asked the question was how much slower and it was a lot slower. So yeah, I would say run things that you can run, and especially for like a QSVM. I think I want to say that's just binary classification. I'm not sure. And right, like you have Qs, right? Q random forest or QRF. There's quantum versions for a lot of these popular machine learning tasks. So they're not, I don't think they're considered deep learning, but they're, yeah, that's a good point. Like don't do other things that'll slow other things down. And then get these to work as well. I try to mix it up as far as like a data re-uploading, and then, you know, a full out, you know, hybrid deep learning, and then a quantum circuit kind of thing.
Yeah.
Okay, so go ahead, Ron.
Yeah, and this whole business of, again, just using the quantum to assist a piece of it seems to be very promising. Even just a normal SVM machine, if you decide to use a kernel function, the weights of the kernel function are just randomized when you start, just like a whole bunch of machine learning programs. At the beginning of the thing, they just run a randomizer and they randomize the weights, and then through the training cycles, the weights coalesce into, you know, some form that's useful. So there could be a lot of these algorithms where you somehow use quantum algorithms to guess at those weights. So you're doing like a quantum guess. You don't get them exact, but if you can get them 75% to what, you know, to where they need to be, and you could do that with just one quantum cycle, then there could be an advantage there, because your training stuff could still take days depending on what you're doing. But if you use a quantum program to set those weights to something more intelligent than just random, you might get your training, like I said, 75% there. That's a big jump.
Yeah, I mean, it sounds like the quantum annealing being done in drug discovery. You know, that's
Yeah.
a initial screening, these types of things. So yeah, like I said, it's like with a lot of these things, quantum's not as exponentially large as classical. So even if you have good results, it's going to take some time, right? You know, you keep telling people like, okay, this is getting greater performance, even though it's, you know, much slower. Let's focus on the physics of the quantum bit and, you know, these types of things. But it isn't important because like a lot of this quantum transfer learning, you know, it looks good on paper, but yes, there's many steps that are not favorable towards speed. So I go back a lot of times, I put in the chat, it's the quantum algorithm, speed, and RAM. So, you know, it's based, and then the other one was embedding classical data. And that one says anything that's like entangling circuits and those types of things tend to get more barren plateaus. So the quantum speed algorithm and speed will be more like, you know, do you have enough RAM to do this? And then, or will it just take too long? Those types of things. Whereas the other one, embedding classical data, you know, is more like, you know, the landscape. So I haven't touched on this too much, but at the end of anything machine learning, you know, when you're taking care of like the nuts and bolts, you have a landscape. So in quantum, you can have barren plateaus, which means it's flat, right? So you want to have wider troughs to go for, you know, optimizations, et cetera. And what tends to happen is if you're increasing qubits, I think this goes for anything real hardware or simulators, is that your trough is getting narrower and it's getting shallower, you know, as far as being a favorable landscape to go down into. So, like I said, I think there's going to be some review. I don't know specifically reviews, but like when people put all this information together and the output is what quantum algorithm you should run, I think that that we're becoming closer to that, because there's definitely the Penny Lane Xanadu research, there's Los Alamos National Laboratory research, and, you know, several others that constantly contribute to this. And yeah, we'll start to see stuff is like, for this application, if you're doing image analysis, this is a better head start than what we have today. Did you have something,
Ron? You know, if you get to a point, might offer some news from the Woman summer school, which I'm in the middle of the first week of. If that's of interest to anybody.
I didn't quite catch the first part.
Womanium summer school.
Yeah, what did you want to do with it?
I said, if anybody's interested in some news from the first week of that, we're
Oh, yeah.
lining up the first week. And actually relative to this group, every day there's been a presentation on quantum sensors. They kind of vary between geodesic stuff, people that are building better gravimeters, and other ones are related to medical imaging, like brain scans and that sort of thing. A lady was there showing off her Darth Vader helmet, so to speak, except it was all white. It's basically a flexible cap. It looks like a swimming cap, and it's loaded with sensors, and their hope is that they will eventually have the same capability as these monster brain scanning machines that look like the space helmet from look like the helmet from Spaceballs.
Yeah, I feel like I'm missing out. And then there was a question in the chat. He says, quantum sensors, Muhammad. So yeah, and I'll elaborate, and other people can too, but quantum sensors have been kind of, they're not new. Like, in order to be considered a quantum sensor, it just has to behave somehow by quantum mechanics. And hence, if you have a squid, which is like, this old squid MEG you'd have in a hospital to do brain scans. And then there was an OPM MEG. So that's, again, like magnetic encephalography. And then right now, the hot one is called these vacancy centers. So they're diamond. And then you omit a carbon and you put nitrogen, and then right next to it has a vacancy, right? Like there's a hole. And then you're doing fluorescence. So you're shining, would that be green light? And then you're emitting red light. And in the middle of this are quantum spins, and it's affecting magnetic information that's going on below, like say in a rat's heart, they've done this. For brain, you have less magnetic information coming out of. So there's silicon vacancies, there's phosphorus vacancies, there's Harvard's really big into this, and they've used it from anything from, I think it's mostly for to get, what is this, like better times. So like a quantum memory, you can use these quantum sensors for effectively. So, and there's, you'll see it for internet, quantum internet, you'll see mixtures of quantum computing, nitrogen vacancy centers, or I think the one I've heard more recently is silicon vacancy centers. And effectively it's for human use or rats use, they're diamonds, so they're inert, and you can place a lot closer than an OPM MEG or squids, essentially, or very effectively. Squids they're super cold, all this type of stuff, you can't get close. So that's the biggest research where I've seen quantum sensors is up against a rat's heart. You get an order of magnitude better, resolution, even though it's not quite as good yet, or this is past last November, or late 2022, because you can get it a lot closer to the subject, that you're getting more of that field, even though it's not, the signal to noise ratio is not quite as good as the other two that have been developed. So there's a lot of this, and you can have a quantum sensor, quantum computer, these types of things. It's a couple qubits, I think. Diamond Quantum Brilliance, I think it's the company, but you'll hear them mentioned a lot. And it wouldn't, like how Ron's saying, like everyday quantum sensing, that sounds about right? So, it's definitely a thing that I've focused on previously, many months from now, before, but it's one of those fields. It's like, okay, it can help a quantum computer. It can help Google's quantum computers overcome noise a little bit, because it's like a quantum memory, and then you can get these quantum effects right away before you have noise is the principal component. So yeah, there's been some pretty interesting studies on it.
So Kevin, I just wanted to mention that you got an honorable mention on opening day of the summer school.
Oh yeah.
We were having introductions, and I'm sure you remember Marlu Sot,
Yeah.
the lady with the tunneling electron microscope, and her work is just so fascinating. So when we had introductions, I got on the cam and said, I'm here because I met Marlu about over a year ago before the first summer school, and she immediately said, oh yeah, it was Kevin's group, he does great things, or something like that.
Yeah,
So,
I might be too far into medical. I don't know. I think I spoke on that too. It was more about how
Yeah.
to network on LinkedIn. That was last year. So anyways, from the tone of your voice, it kind of sounds like, oh, everything's coming together in quantum. Again, it felt like that last year. So everybody's waiting for the killer app to come out, or the good application, as you might say. Anybody else that we haven't heard from? So feel free to post in the chat. You could also come on, or you can unmute yourself. And yeah, there'll be, I remember watching that and going back to Womanium last year. It sounds like it's every day now, and it goes on for a while. And there's I think there's a fair number of interns that they'll have. So those types of things.
yeah, it's 3+ hours every weekday in July.
Yeah,
And
you can
and-
post
and-
a link, because I'd be curious, because I
Yeah.
haven't caught it. Like, I'm really focused on the medical stuff. So
Yeah.
yeah, it's definitely worth checking out. Lots of experts, I would say. I think Worley, his name's William Hurley. He's CEO at StrangeWorks. He's already been on. And last I recall from last year is you just go to womanium.org, and then they'll have a link to YouTube, and then you can just do live streams and catch up on previous speakers too. But yeah, it's a big thing in the quantum world, but it's still, as a whole, I was watching a couple of these Cleveland Clinic and IBM, they installed the first quantum computer in healthcare. And some of the things is just like, it can do this and it can do this. It's like millions of, it's so much faster and all this stuff. It's just like, well, it's not quite what I experienced, hopping onto simulators and notebooks and these types of things. But the buzz is there, right? If IBM trusts the technology enough to put it into a healthcare system, and the healthcare system embraces it, Cleveland Clinic, this is a huge thing, right? And that can't be discounted, even if that current quantum computer, can't do, thousands of data sets and, hybrid with machine learning, those types of things. And there's so NYU Langone has partnered with Fermilab, and they're working on brand new MRI analysis with quantum sensing, as we mentioned before, and quantum computers. So that'll be interesting. I came across some NIST articles, even, 15 years ago, something like that. They wanted to have a quantum sensor at the tip of a probe. And then so you wouldn't need this full out MRI, just because you can. And I think this is it. After reading these, you can get the tip of the probe a lot closer to the human, because with an MRI, you have, liquid cooling and all, if it's nitrogen or helium. And anyways, there's a lot of space between a patient and the magnets spinning around. So yeah, I wouldn't be surprised if we'll start to see that, like a lot of these prototypes, as far as bring a sensor closer to the heart, which is the main, the biggest source of magnetic information, and then start, going into the brain, and then quantum images and all these types of things. So yeah. So in the Qiskit, I know the Qiskit, the IBM summer school last year, Ron, it was error correction school. So imagine sending, your son or your daughter, it's probably more like your graduated, like PhD or whatever student. that they go, for Kiskett Air Correction School. I haven't caught the name of it this year. But yeah, he says it's free. And there's just tons of stuff to do. You just keep the ball rolling. If you're not running models and, programming in quantum, take courses. To me, you won't get too far unless you're programming. Even as CEO, that's what I primarily do. And then I'll catch a lot of classical talks too to help me with the AI, what's going on with Tesla and such. But it's kind of like you imagine how the world's going to be, and you can have an impact on it, right? So pick a subject, finance, medical, transportation, what have you. Pick a subject, and I highly suggest running demos and reading papers, changing your algorithms, getting a better understanding. You're probably not going to get anything awesome at first, but it's in that right direction. So. But I get that sense of going to other Python, I go to other deep learning, machine learning groups. They don't really want to learn quantum computing, right? They're big cities too. And they said, can't we just plug this in? And I said, well, you can, but to get the best results, you're probably going to have to, be like a good machine learning engineer and study it and, make changes that make sense and have a high probability of them being better, better results. So yeah, there'll be those that will be very late to the game that are just completely convinced in classical, and you can go to many groups and they still don't, their city hasn't caught on or they haven't caught on. It's common.
Yeah, I think we've noted that actually. I've noted that with most of my colleagues in the machine learning field. Most people coming from computers, from a more computer, IT and computers background, are kind of hesitant with quantum, but I think we're seeing because I'm in a community, a quantum community here, and we're seeing excitement from people coming from the science fields, the like physics. Yeah, such people are excited, but yeah, it's really strange. Yeah.
I mean, the other sense I get is some people is like, okay, I'm just going to study quantum computing, but that's typically not how things work. Like you have to be an expert in at least 2 fields. So if you know something about machine learning, just how it works, but more about quantum computing, to me, if things go well, you're going to be in demand, right? Because there's many deep learning scientists that probably won't take the jump to quantum, right? Like the full jump, like many of us have already taken. And, in order for you to be essential, when the starts really hitting, better hardware, better simulators, those types of things, and better understanding of how data moves through qubits with physics, those types of things, is that would be a good area in my mind. It's just the question of time and when, and NSF said practical quantum computer this year. I think other manufacturers don't know what that means, right? As far as like the actual performance that they'll be at, but yeah, I mean, it'll start in my opinion, reading these papers, mostly quantum, but some hybrid or even just classical, is it'll really start hitting with the deep learning community, like is engaged with quantum. Like they're staying up late at night to study gates and, circuits, these types of things. And then they can see on their own the weaknesses of deep learning. And, this, like Ron had mentioned before, this would make sense as pre-screening here for, the quantum algorithm, that type of stuff. Because they have, Andrew Ng and others, Kevin, I'm trying to think of his last name. I think he's at Stanford. So basically, they have a very good understanding of data. And if you watch a lot of the deep learning calls, like on YouTube, one of them will just say, this is a computational complexity. Like this would just take way too long for us to do. They won't mention quantum. They'll just say like, it's a known issue with the mathematics of what they're doing. And then they'll start to understand, okay, we can put quantum in here now. So that type of stuff. But it's still kind of niche, it's because even if you have awesome results and publishing, and very interesting results, like compare against several other classical networks and have very good conclusions. It still takes a while because the majority of people just don't, it's still complex, right? Like watch newscasts where the IBM and Cleveland Clinic, they'll announce the quantum computer. Two of the reporters have no clue. The other one's just like, it's amazing. It just fixed everything. So it's like, it's more about papers and research and, these specific things that you can do.
I think just before,
yeah, go ahead.
I'm seeing this paper by Nature. I think it's from one of the schools that you often mention on this talk, the Los Alamos lab. They've printed a paper on Nature called "Out of Distribution Generalization for Learning Quantum Dynamics," and it's kind of interesting. It came out only like a day ago, only maybe barely 24 hours ago, on 5th July. And they're talking about the requirements, the data requirements for successful quantum machine learning, and the saying needs to be it needs more simple data. Quite interesting.
They come up with really interesting papers, I would say. Because I think one of theirs is like few generalization from few training data. I think it was, QML or quantum computing, but that sounded interesting too. But it's just, there's a gap, right? Because you read a lot of these papers, is just like, well, how do I apply that to what I do? And sometimes you can say, okay, well, maybe I shouldn't do that, like with a CC or, CQ, or most of these are, classical learning, quantum hypothesis, algorithm type of things. And I learned the most if I just try it. Especially, I probably learned a lot more about machine learning at times running hybrid models that I just had the single circuit at, weight decay, and do I want to skip connections, or, these things, and you can change in other networks essentially. So yeah, and it's just not giving up. There's ample resources out there. I'll get frustrated because I'm like, well, how do I get my 88 qubits for 44 classes when I'm only at 20 qubits, and I go to 21 and I just get an error, where it should run, those types of things. But there's a good flow, there's a good output of papers, especially archive papers. They're not peer reviewed, but they're faster, right? So in Nature is like peer reviewed, all this stuff is kind of slow. But archives tend to be like cranking out, quantum's not perfect, but just get it out on paper, we'll figure it out, kind of thing. That's my opinion of it all. And yeah, I mean, World Quantum Day was in April, so I didn't quite hear too much about it. I'm more in papers and running, algorithms and that kind of stuff. But IBM has a ton of resources, and Ron or others could probably tell you that there's a book out there for Qiskit, and it seems like it's narrowing down, because Qiskit is they have our Qiskit plugin will work on PennyLane. And they're two different, and the whole open sourceness. But by and large, most of it seems to be the Xanadu's PennyLane for the QML kind of stuff. And they just added support for, multi GPUs. And I know you could do a lot of awesome stuff on AWS. It's just, it tends to be paid, right? So yeah, that's been my experience. Anybody that we haven't heard from? So Victor, Muhammad, or Anand, or George. So you could feel free to unmute yourself, or you can come on as well. And just keep your eyes peeled, because the way it's been going in 2023 is we'll hear some pretty good announcements, like Quantinium, 32 qubit GHZ. Which is I think it's 3 qubit. It's multi-qubit entanglement. So a significant task for a quantum computer to do it, accomplish. Google, like I said, they got the same kind of fidelity for like a 40-something qubit compared to a 10 qubit. Actually, it was lower for 40 something qubit. And yeah, that's fine. I mean, digesting the new stuff as well. But I would say for the future, and I've been in this boat before, it's just, just doing the news and cheerleading and all these types of things, is that I had to learn machine learning, and I had to learn, quantum circuits and gates and algorithms, and it wasn't easy. And I'll still go back and rehash that stuff. But if you need help, if anybody has any questions about, Jupyter notebooks or Qiskits are free. I'll even run other things on Qiskit just because my local Jupyter lab notebook's not working, and then my collab charges me, but I don't need it because it's only for my GPU stuff, right? But I'd be interested in it. Yeah, anybody has any questions about coding, how to get started, running the models, those types of things, you're gonna get, in my opinion, the farthest down the road, right? Yeah, so go ahead.
Do you need GPU on when running quantum algorithms on Colab?
It just depends on the notebook, right? So I'll give you an example for the quantum transfer learning one. The GPU I tried to keep it at V100, meaning that's like the mid-grade, and an A100 costs more, like, like you're constantly putting in more credits. So yes, so in a hybrid notebook that's doing all this stuff, and at that same time, somewhere in the Ethernet of internet, it's doing it's called a default.qubit. I couldn't get lightning.qubit to work in that model. So anyways, there's a lot of talking going on between the simulator and the GPU, right? Like it does that test, that does this. So I might get like a 10x slower between all that, even if the performance was a little bit better running quantum, and it's like whatever. So yeah, a lot of the smaller models, like the QDIT model that I put from Circ, that one in specific, I ran last night, and it on my collab, so it's just charging me a little bit, but I didn't need a GPU.
Okay.
Yeah, so when you start thinking about your model, like how much data do you have? Like, so if I jump from 3,500 to 4,400 in images, that's going to take longer, actually, when I jumped from 10 classes to 44, that didn't do much at all, right? Like it's not the classes, it was more like the sheer amount of data that has to go through the deep learning neural network and the quantum algorithm.
Okay.
And you also will run into this, it's the first epoch. And so in machine learning, so if you have batches of data, they have to run through the neural net typically. So say if you have like it takes there's batches and batch size, right? So if you pass like 10 images at a time and you have 100 images, so you have to do that 10 times. And then at the end of that, that's the first epoch. Now that first epoch is really slow with quantum simulators. It's called initialization. So a lot of times I'd run a smaller quantum circuit to get the initiation time down. And then the second one, I'd run the circuit that was bigger that I wanted to, because it's basically for training and validation, those two steps of that epoch, each of those has to go through initialization. So you have to be aware of these things. There's just certain things that aren't 100% optimized now.
Okay. Thank you.
Yeah. So, and the bigger the quantum circuit, the more data, that type of stuff. But, it's in theory, if you don't disconnect and delete runtime in like Colab or AWS, you can have a good bill. So you want to do that too. And there's little pieces of code to connect a Google Drive to your Colab. And then at the end, if you want to disconnect and delete runtime, there's another one for that. So it's a learning curve if you haven't done machine learning, I would say. Awesome. Anybody else? Appreciate everybody coming on. This is discussion 90, July 6th. Happy holiday week, everybody. It will be fragmented this month because people take vacation at least one one week out of the month, at least out here. July 6th, 2023, for quantum algorithms and deep learning pairs for medical analysis. Appreciate it, and have a good rest of the night, and have a productive rest of the week. Take care, everybody. Bye.